Alrighty. Once Alex pops on, we'll get started and I'll get us kicked off. Oh,
Here I
there we
am.
go. All right. Well, good evening, graduate UNSY students. First, just for everybody's awareness, we are recording this session and a copy is going to be made available to those who are unable to attend live. Next, for the format of tonight's meeting, I'm going to start by introducing our guest, who will discuss his connection to uncrewed and autonomous systems sensing technologies. After, I'm going to lead a series of introductory questions, and then we're going to open up the session to a class-wide Q&A. I do ask that everybody mute your mics and save any questions to the end. And when we do open up that Q&A, use the hand raise icon to indicate when you do have a question. I'll call on each of you in order. And with that, I am just thrilled to welcome you to the 37th session of the UNSY Guest SME Speaker Series. This is the first of 3 for the term. I'm Dr. Brent Terwilliger, the Program Coordinator for the Master of Science in Uncrewed and Autonomous Systems degree here at Embry-Riddle Worldwide. Tonight, we're joined by our guest subject matter expert, Dr. Alex Lussier. Dr. Lucia is an application engineer at Resonant Hyperspectral Imaging Solutions. His work involves assisting professionals from various disciplines to understand hyperspectral imaging and how it can be used to address scientific questions and solve industrial challenges. Alex has a PhD in physics with expertise in material science, spectroscopy, and education. He has spent half his professional career in academia and the other in industry. These days, he assists users with all aspects of hyperspectral imaging, including feasibility studies, data acquisition, which includes laboratory measurements, land-based outdoor measurements, and airborne imaging, as well as data analysis. And with that, let's give a warm welcome to Alex. I'm excited to turn the stage over so he can share some details about how Resonon is helping to shape the future of uncrewed sensing and imaging.
Thank you very much, Brent, and welcome everyone. I'm happy to be here and chat a little bit about what I do. Thanks for the introduction. I don't need to do anything else now. Guess we're ready to go. I'm going to share my screen here. I have a PowerPoint presentation that I think should last somewhere around 20 minutes because that's what I was asked to prepare, and then we'll go ahead with questions. So I'm going to share my screen, which is this one over here. Okay, so you should be seeing my screen that says Resonant Hyperspectral Imaging Solutions.
Yep.
And I will go ahead and get started. So I put a short outline together so that you can see what's coming at you. So I'm going to just talk a little bit about the company and then also the technology because hyperspectral is not familiar to many people. And then talk a little bit about our products and the applications, and then dive a little more deeply into airborne systems because that's what is of interest to you. And then the data acquisition process, which I think is also going to be perhaps interesting. And then regulatory implications, because I think that was something that was of interest to you. Interestingly, I think I might learn more from my audience than you will learn from me, but I'm going to put one slide in there to talk a little bit about maybe some of the challenges and some of the things that we need to think about and that maybe we're not thinking about enough. And so we'll talk a little bit about that at the end. So our company is called Resonon. We're located in Bozeman, Montana. So I don't think if you see my cursor right here, we're just above Yellowstone National Park. And we're a company that's been around for about 20 years and about 15 people in Montana. And we build all of our imagers here. And we sell our products in North America directly. And then we rely on a network of international distributors to sell our products everywhere else around the world. And so here's my introduction now to hyperspectral imaging. It is imaging in the same sense that you think about photography in general, but kind of on steroids. So first thing is that if you want to image an object, for instance, I have a cartoon tree here, you need to illuminate it with a source of light. And a lot of times you can rely on sunlight. If you're indoors, then you need an artificial source of light. But then this light that comes to you, I'm going to talk about this in a little minute, but that light is reflected off of the object, and then you detect the reflected light off of the object. That's how you record an actual image. Now, the light that comes to us, for example, from the sun, has a certain spectral distribution. So most of you have probably at least seen this before. I have the electromagnetic spectrum over here. All of this is light of different wavelengths. And so very short wavelength and high energy light is gamma rays. And then X-rays, ultraviolet is just below the visible in terms of wavelength. And then you have the infrared. It's just a longer wavelength of electromagnetic radiation. It's the same thing as the visible light, just a longer wavelength. And so are microwaves and radio waves. But the light that we get from the sun mostly is found right in this little part of the spectral ranges of light, and it has a distribution. This is a bit of a cartoon, but it's actually fairly accurate. This is the distribution of the light that comes from the sun. So short wavelengths we get a little bit, and then we're in the blue and green, it peaks. We get a lot of light of those wavelengths, and then it tapers off over here. And then once the light is reflected by the object, this object absorbs some wavelengths preferentially and it reflects others. And so if you look at the incident light with the dashed line here, this is what came at us. But then because this object has different chemical bonds that absorb different wavelengths preferentially or reflects them, what you get is maybe something like this. So if you take an image with an RGB camera, just a standard color camera, what you measure is basically every pixel is actually composed of 4 pixels, and one of them is sensitive to blue, one of them is sensitive, or two of them are sensitive to green because we get a lot of light there, and then one of them is sensitive to red. And you measure the amount of blue light in a finite range of wavelengths over here. So blue is centered around 460 nanometers. So you basically capture everything between 440 and 470 maybe nanometers, and you say, okay, I'm calling that blue light, and then you capture green and red. So out of all this fine detail in the spectral composition of the light, you're just measuring basically a 3-bar chart. So what we do with a hyperspectral imager is instead of measuring 3 channels, we use a clever way to separate this into many, many hundreds of channels that are very narrow in width, and we measure them all individually so that you can actually measure and reproduce the exact shape of the spectra of light that's reflected by the object. And then we do this for every single pixel in the image. So one way to think about this, if you're familiar with spectroscopy, is that basically we're taking digital imaging and we're putting it together with spectroscopy, and we're doing it all at once. So if you take an image with a hyperspectral imager, you get an image, say, that looks like this. For every single pixel, you have a complete spectrum. And now you see that the additional information that you get from this is that, for example, if you look at the green in this field over here and the green in this field over here, to the naked eye, they look very similar. I can tell that the one up here, crop number 1, is darker, but to the naked eye, I would say that crop number 2 and number 3 look really quite similar. And that's because they're basically similar in their ratios of blue, red, and green if you're taking an image only with the RGB camera. But if you have the entire spectrum, then you can see that between crop number 2, which is the red spectrum, and crop number 3, which is the blue spectrum, I have some very distinct differences over here where crop number 3 has a bigger peak here. This is actually a chlorophyll peak over here. Well, the fact is that chlorophyll absorbs over here and it doesn't absorb as much at these wavelengths. And that's why green things look green. And then you have other peaks, and then you have some water absorption peaks in there as well. But in any case, you do have contrast there. So you can use that information now to tell the difference between this crop and this crop, or maybe this crop that is in good condition or the same crop that is lacking water or something like that. You have very, very careful measurement of color. And you have that for every pixel in the image, and it allows you to do some really powerful analysis. So let's see what my next slide is. There we go. Talking about our products. So I just put the electromagnetic spectrum up there again because we have multiple imagers. We have, I think, 8 right now in our that we're offering, and some of them function in the UV range, so a little bit below the visible. Some on the visible range, actually visible and near infrared, so visible and a little bit into the infrared. And then we have imagers that work in the what is called SWIR, is short wave infrared. And the infrared range is really quite wide. You also have the mid-range infrared and the long-range infrared, and you can make imagers that work in those spectral ranges as well. And the reason why you want to have different imagers that work in different spectral ranges is because some of the chemical signatures that you see, some of the chemical bonds and the reflections that you see, you'll get more contrast in one spectral range than in the other. For instance, for plastics, for plastic identification, the infrared range is really very useful. Then besides selling the imagers, we also have software products for data acquisition and analysis, and 2 different kinds of software, and then analytical software. This is just a screenshot here of our software called Spectronon, and this is used a lot in research lab and some kind of pure analysis kind of application. And then this is a screenshot from our machine vision software. And so you can imagine this, for example, is a training screen. We're training the system how to recognize the difference between almonds, almond shells, and chipped almonds. And because they have distinct spectral signatures, which you can see over here, we can classify them in real time. And so you can have a stream of these things, of a mixture of all these things driving down a conveyor belt, and the system is imaging them in real time and telling your robot, at this location there's a shell, blow it out of the stream. So that's the kind of thing that we do. And we to do this, the imager itself is really just an imaging instrument. It has an objective lens, a spectrometer, and then a digital camera, but you need to control it with a computer. And you also need a system, a scanning system, because all of our imagers are line scanners. And I'll talk a little bit more about that in a minute. So I'm just going to dive a little bit deeper into these different scanning systems now. So there are line scan imagers, meaning that they capture a single line of pixels at a time. So if you want to get a full 2D image, you have to basically stack multiple lines together in order to get a full 2D image. And so it's a little bit like when you feed something into a fax machine, or if you take a photocopy, you see the light traveling and it's captured one line at a time. So it's a bit in the same way what it's doing. And we have to do that because we use a clever method to capture all that spectral information in addition to the spatial information. So when you acquire data with a hyperspectral imager, you acquire what we call a data cube, because you'll have 2 spatial dimension and also the spectral dimension, which is hundreds of channels of spectral information. So if you use a benchtop system like this, you put the sample on this translational stage, and the samples are scanned below the camera over here. Here's a light source, and then you can capture data that way. For the outdoor, instead of scanning the samples, because of course you might be looking at trees or mountains or something like that, you can't put them on a scanning stage. Well, in this case, you can put the imager here on a rotational scanning stage, and so it'll scan across the landscape and capture a full 2D image that way. If you're using it in an industrial setting, such as where you're sorting fruit for ripeness or damage or something like that, then you put the imager on top of the conveyor belt, and the conveyor belt provides the scanning motion. In airborne case, then the actual motion of the aircraft is what provides the scanning motion. So our airborne system consists of first the imager, which is over here, and then we package this into basically the airborne acquisition system. So we have a data acquisition computer, which controls the acquisition of the imager. We have our own GPS IMU, so we don't tap into the GPS of the of the drone or aircraft. We have our own, and so our bundle here functions completely independently of the aircraft that it's flown on. And these are used for all sorts of applications like precision agriculture, environmental monitoring, gas detection, mining exploration, and basically your imagination is the limit here. That's actually a really interesting part of my work, is that I get to talk to people in all sorts of fields, from people who are doing precision agriculture to brain surgery to sorting plastics and waste material, because the applications are really all over the map. And I think that it's become more and more mainstream, and people are starting to understand what you can do with a hyperspectral imager that you can't do with other types of imagers. And so I think it's just going to continue to grow in applications and usage. So as I said, our system runs independently of the aircraft, but drones are a very common way to acquire airborne data with our systems. And so we offer a small kit that adapts to the DJI M300 simply because it's a super popular drone and many people want to use it. And so we try to make it easy for them. We have also partnered with a US drone company called Vision Aerial. And there are two reasons for us to do that. One is that it's nice to be able to offer a completely integrated solution so that the consumer doesn't have to go shop for a drone and also shop for a system and then find somebody who can put it together, which in some cases can be beyond the technical ability of the customer. So now we've partnered with them and we offered a completely integrated solution. There's another important reason to do that as well, is because the DJI drones, as popular as they are subject to some restrictions, especially for government-funded applications and things like that. So we're quite happy to be able to offer these solutions to our customers now. Okay, so a little bit of how this works. So before you even go up and acquire data, you need to basically prepare your data acquisition. And the first thing that you do is that you log into our ground control, or our Resonon ground station software, and you can upload into there a KML file that you generate perhaps with Google Earth or something like that, to basically represent the area of interest where you want to acquire data. And so this would be, for instance, the blue screen, the blue rectangle here. This is where I want to acquire my data. And I create my KML file. I go a little bit outside of that just to make sure that I capture all the data that I need. And I upload that onto the system. And what that acts as is basically like a geofence. And so once the system is up in the air and it knows because of its GPS that it has entered the area of interest, then it starts triggering acquisition. And then the path that you fly, that's you do with your own software. Most drones now have some kind of flight path tool where you can generate a flight path with the distance that you set between passes to make sure that you cover the ground. Of course, you could do that in a manned aircraft or crewed aircraft as well, and then the pilot would just be responsible for flying in a pattern that covers the entire ground. We like to say it can go on anything, including an air balloon, and actually it has. So really doesn't matter. It functions independently of the aircraft that you use. So once you do this, upload your target area and also establish all your acquisition parameters, because you need to adjust the frame rate and the exposure time for each frame according to the light conditions, how fast you're flying. Make sure that you obtain square pixels if you want to get square pixels. So it's all included in the software, so you can program everything and get ready to do your flight. And then once you do that, there's some pre-flight checks that you do to make sure you have all your GPS signal is good, and then you basically send the drone up on its flight path. And this is what this might look like. This is a farm that's just basically a few miles away from here, and you just fly over the field, and as soon as it enters the target area, it starts acquiring data. And then you can see what you obtain here. And I'll talk a little bit more about this image over here at the end to basically when I talk about what the data analysis is that we do and what we can do with this data. But again, yeah, GPS location used to trigger acquisition. The data is recorded on an external solid state drive that it just attaches to the side of our airborne acquisition system, so that once you land, you can take the data from your solid state drive, just plug that into your laptop or computer, upload the data, and do your post flight post processing and analysis. So in a lot of applications, flying about 100 meters above ground is pretty common, but really there's no limit. It just depends on the kind of resolution that you want and the aircraft that you have available. So crewed aircraft are possible, and we even have some systems in space. We don't have a turnkey solutions to put on a satellite, but people have used our systems to go in space and do some measurements as well. Okay. Let's see, next slide. Okay, so then as far as the post-processing goes, as I mentioned, you were just acquiring lines of data and we're stacking them next to each other. And because a drone or any kind of aircraft doesn't fly a perfectly smooth and straight line, you get something that looks a little bit like this. But what we use is the information from the GPS and IMU that we recorded at all times while we were flying. We know exactly which direction the imager is pointing when it's taking this line and that line and that line of data. And so we can rearrange that in a process that we call georectification. And so this is done in post-processing. So now you can see that all the lines have been unscrambled. If some of them overlap because the aircraft tilted forward and back or something like that, takes care of all of that. And north is pointing up, and also a geotiff image can be generated, and then you can plop it into to Google Earth if you want with the correct longitude and latitude. So if you're doing, for instance, precision agriculture, you may want to overlap that on your field and know exactly where you need to apply more fertilizer, where you need to increase watering, or whatever it may be. All that information is there. And that's done in our own software. There are some third-party software packages that you can use to do this as well, but we've written it into our own software, and you get that when you purchase one of our systems. The other part of data processing is basically has to do with illumination, because our measurements are very sensitive to illumination. So what you really want typically is to get reflectance data. So that means you're calculating exactly the percentage of light that is reflected at each wavelength. And so if you want to know how much light is reflected at each wavelength, you need to know how much incident light you had at each wavelength. And so there are different ways of doing that. One way is to use an additional sensor on top of the aircraft to measure at all times how much light is coming. So you can do that normalization. The other way is to put a calibration tarp on the ground before you image your area. And then since you know the exact qualities of that tarp, its exact reflectance quality, then you can use that to backtrack how much illumination was in there. But that's all really important, because what you don't want is to have a measurement where you can't compare it to what you took yesterday, because yesterday was a cloudier day or something like that, and then you can't compare your data. So you need to always normalize your data. That's really important. I just mentioned in passing here RTK. So for people who need very high geolocation accuracy, we have an optional RTK as well. Again, we don't tap into the RTK or GPS system of the drone. It runs completely independently. So, okay, next slide. So what you get is an image something like this. And so because the drone wasn't flying perfectly straight, you get an image that has some wiggles in it. But in this case, what we probably had is this area over here that we want to make sure we get data in it. and then we go ahead and fly, and then you get a little extra on the sides. If you plan your mission right, you still get all the data you need. And you might use this now to go probe. This is just an RGB rendering now, so it's not an actual hyperspectral data file. I'm looking at PowerPoint, and so it only has 3 channels in there, with red, green, and blue. But if you were doing this in our software, you could click anywhere on there and look at the spectral quality of each pixel in there. And so you could use this for different applications, such as looking for damage on your rooftops, or for looking lack of moisture in your field in some areas, or looking for algae blooms in this lake, or maybe trying to do some kind of survey of the tree species that you find here, because they're not all of the exact same green, and you want to find out maybe what's the percentage of oak compared to the percentage of pine in this forest, or something like that. Or perhaps you've trained your system to recognize the difference between a tree that is healthy and one that has been diseased because it's been attacked by a bug or another. So you can do that all in the software. The the next image is one that you saw earlier in the video. In this case, all that's been done to this part of the image, it's been overlaid on Google Maps satellite video, and then you see, okay, on top of this Google Maps satellite video, this is the area that I've done a hyperspectral survey of, and this looks to me like is a principal component analysis. So you don't necessarily need to know what you're looking for. You can actually use some software tools to basically reveal some contrast that exists there. And so this is what this does. In this case, it says, well, based on the mathematical algorithm, it can tell that what's growing down this row here is definitely growing different than what is growing over here. Um, that is good for exploratory research. A lot of times when you're doing research, you know what you grew over here, and now you can go say, okay, now I'm going to use this as a reference, and I can go recognize that elsewhere in the field, in another field, on another day, or something like that. And you maybe have identified that these yellow patches are weed, and so next time you fly over a field, you can apply the same transformation, the data transformation to your images, and go find exactly what you're looking for. Okay, so hopefully this gives you a bit of an overview of what the technology does and how it works. And I'm just gonna, this is more like a suggestion of what we might discuss that might be interesting for you. So regulatory implications for us are actually largely left to our customers. So we don't fly the system for the customer. We don't offer survey services. We really provide payloads. So we provide hyperspectral systems, and yes, we help them acquire a drone to fly it onto, or we help them adapt it to whatever aircraft they have. But largely, it's their responsibility to figure out how to use this legally, basically. So for a lot of them, it's just getting their drone pilot license in the States. And we actually on our crew only have one person who has this Part 107 license, and we still don't fly the customers' drones because we don't have the insurance to cover ourselves to do that. But we'll still even go do some trainings on site with the customer and let them fly their own system, but tell them, okay, this is how you set up your data acquisition, do the data analysis, et cetera, et cetera. But beyond that, we sell our systems all over the world. So certifications are definitely on our mind in terms of other customers around the world. And by certification here, I would say not just in terms of flying, piloting the aircraft, but also just CE certification, for example, so that we can actually sell our instruments over there. And so we need to help the customer pair with a drone that they're allowed to use where they live, et cetera, et cetera. So there's definitely some implications there, and we kind of leave it up to the customer, but it's certainly good for us to be aware of what is and what we need, what is a concern for the customer, so we can help them out as best as we can. And then I thought it might be interesting to just point out that data acquisition occurs in different areas for different applications. And so really our systems are kind of flown everywhere. Sometimes it's very remote, like forestry, mining, environmental monitoring applications. Actually, environmental monitoring can happen everywhere, remote, rural, or urban environments, but definitely agriculture is in rural, and then urban if you do infrastructure inspection or something like that. So it's something that our customers definitely need to worry about. In all sorts of environment. We live actually pretty close to an airport, and so our one person who is allowed to fly our system to do some testing, he does it here, but we have to fly low enough. We're not right next to the airport, but close enough that we can't fly over. I guess it's 400 meters, I think, or maybe it's 400 feet. Um,
Feet.
yeah, feet. Yeah. So the one person who's certified is not me in our company. So okay, so that's I hope that was short enough but long enough to give you a sense of what's happening. And so yeah, I'm more than happy to have questions and discussions.
Outstanding. Well, I'm going to kick us off with a few, and I think we've got some folks that are chomping at the bit already to go
Okay.
ahead and ask. Uh, all right. Do you mind dropping the
Yeah, I'm
excellent.
going to shut that off. Let's see. Oh, I think I'm still sharing my screen. Sorry about that.
No
Where did it
worries.
go? Oh, right there. Stop share. Okay, there we go.
Perfect. There we go. Uh, so I definitely like to reinforce one of the notions you had up was exploring some of the certification requirements outside the US, globally, worldwide. And that is definitely one of the more challenging aspects of navigating this space because Part 107, the certification that goes with that for your RPAS, it's not reciprocal. So, if you look at, say, radio certification and licensure, that is reciprocal across nations. Even conventional, you know, uh, private pilot's license, etc. Those are fairly reciprocal. But for some reason, we haven't gotten there yet with small UAS or RPAS credentials. Hopefully one day, but for now, everybody's still, I think, trying to get their head wrapped around the utility of the technology and the way that they can manage it effectively. I'd like to ask, what are some of the challenges or breakthroughs that you've encountered in applying hyperspectral imaging with a UAS? What might have been kind of surprising that you encountered?
Um, I think one of the big challenges for us is that people are hoping for a turnkey solution that does exactly what they want. And typically we we can't offer that because every application is different, and so you really need to have people who are willing to sit down and use your system and train it to do exactly what they're trying to do. So I think that for instance, precision agriculture, there are now some service providers who can use RGB cameras or perhaps multispectral cameras who have like 5 spectral channels, and they're starting to have that pretty well nailed down in terms of, oh, there are these um, they're called indices, and so they just use a simple algebraic operation between different spectral channels and say, this gives me a pretty good sense of whether I have good chlorophyll in there or not, or something like that. You can get a lot more out of hyperspectral system, but you also have to put in more into it to train it to start to figure out, use the full potential of the technology and the massive amount of data that you have, because basically you have about 100 times more data to work with, which can be really useful, but it's always a bit of a step in order to get things to do exactly what you want. And for that reason, a lot of our users are academic research people, because they're willing to put in that time and figure it out because that's their business. That's what they do. Um, but then getting into the industrial market and selling systems to, I mean, we'll probably never sell a system to a farmer. Well, maybe not, definitely not in the near future, but it'll take some work before we get there. So that's probably the biggest thing is basically the work that needs to go into a new technology like that. That's pretty heavy on data analysis and training.
Excellent. I assume you're using or you've seen the use of AI technologies to help with that sortation, categorization, recall of
Yeah.
data. Uh,
Yeah, so we don't use AI per se, but we use machine learning algorithms in order to crunch that data and get some good information out of it. Because you can render your image in three channels that you want, and our eyes are actually only able to process three color channels. But if you want to do something with 100 channels, then you need to crunch it in some way. And so we use basically they're standard mathematical algorithms that are applied to hyperspectral data. And so we definitely use machine learning models, not so much AI, not at this point.
okay.
Yeah.
You mentioned Vision Aerial to help put together turnkey solutions for customers that come in and need help getting, that aerial perspective. Can you share some examples of other partnerships or collaborations that have been essential in expanding the use of your products?
Um, yeah. So a lot of times some of these collaborations have happened because customers come to us and they'd love to have a turnkey solution. And so maybe they find a drone provider or a drone manufacturer who's willing to do the integration. And then we work with them to do that. There is a drone distributor in Canada who had that, and they're called Infinite Drones, and they've worked hard to develop basically a department that helps do that integration. And so you need to have somebody to commit to doing those integrations, um, to really make things happen. And so those collaborations with either manufacturers or resellers that are putting in the work are really useful for us in order to be able to reach customers more easily. And these typically come from basically existing customers who have contacts in different places. So, yeah.
Excellent. So, how has your background helped to shape your approach to hyperspectral imaging technology use, including outreach and implementation?
Um, well, yeah. So as you mentioned, and I think I talked about it briefly as well, my background is in physics, and so it wasn't in optics or anything like that. And I'm here, and I don't design the optics in our systems either, but definitely physics is kind of a good background to understand the physical processes, the interaction of light and matter, and also just anything that comes our way, like understand the plastic bonds and the chemical bonds in plastic and how those are revealed by our spectroscopy techniques and things like that. And so um, that's really useful to tackle or to be able to assist customers that come from a wide range of environments of expertise to help them see how hyperspectral imaging can help them. Um, in terms of outreach and things like that, in some ways, I'd say I feel not that well prepared. We each have our strengths and weaknesses. And if you told me that I would be in more or less a sales position at some point, I would have thought, no way, I'm a physics nerd. That's never going to happen. So there are definitely parts where I'm learning still. But physics is a good general background that helps me with our customers. So that's always good.
What advice would you give to graduate students who want to advance their skills in this field? What cross-disciplinary knowledge is just an absolute must-have?
Like specifically in hyperspectral imaging, or
Yeah, yeah, as
yeah,
it relates to UAS.
yeah. Um, I think uh, almost for sure there are some hyperspectral imaging systems that don't scan, that are not line scanners. They still scan, but instead of scanning one of the spatial dimensions, they scan the spectral dimension. And so it's basically like taking multiple images at different wavelengths, like a full 2D image at one wavelength, at another wavelength, at another wavelength. But that is not very common. Almost all hyperspectral systems are use a line scanning approach, and so understanding what the implications are that are of line scanning in an airborne system is fairly important, because you're basically going to come up against that almost for sure. And so it's a different type of, for instance, if you take regular image, a 2D image, and it's a snapshot image, and then you take multiple over your area of interest, then you have to stitch them together. But that's a different stitching process than what we use. We use the actual orientation of the of the um, of the imager when it's taking, because you don't have enough in a line to recognize and start matching patterns or anything like that. It's just not possible. So that's one intricate thing that probably you won't find in a lot of other fields in terms of UAS is that. And like, we have our own software. There's a few other third-party companies out there that offer software to help you do that, but um, it's not a simple task, and you just have to know how this all works.
So
So
yeah,
I
you
guess,
have to use a transformational matrices calculation
yeah,
connected to the IMU to figure out, where relative everything is so you can stitch it and
yeah,
interpolate.
yeah,
So
yeah.
yeah,
And
it's
when the first project that I worked on when I came here was actually, not only do you need to know where it's pointing, but you need to maybe know if it's actually slightly misaligned with your IMU. And then you'll get a systematic error out of it. And so then using some data to try to figure out what your systematic error is. And so you can put in those parameters in the software to correct for that slight misalignment, even though it's all bolted together nice and tight. So that was one of the first projects that I did, which is a really interesting project, actually, is figuring that out. Definitely put my brain into some gymnastics, but it was really interesting. So, but I think there's lots of opportunities for people who are experts in drones and unmanned aerial vehicles, because there's more and more being done. For us right now, our airborne business is about 30% of our business, but I think it's probably going to grow. And I think there's definitely room for people who want to become service providers, like I mentioned, in precision agriculture, or perhaps in forestry surveying or mining surveying, looking for prospecting or things like that. Um, there's only the really big players who are able to buy their own system and have the expert to run that system. But if you are interested in one of those fields and you can learn how to use the system, then you can sell your services. So as a student who might be interested in flying drones and doing some interesting work with it, I think that's an opportunity that would be really interesting.
outstanding.
Yeah.
Well, with that, I'm going to open up Q&A to the students. I know somebody had asked if they could come on via video. We do have one from Christian, where earlier he asked, can you adapt your software for this to an open source tool or platform like Pixhawk?
I'm not familiar with Pixhawk. Our standard software is actually downloadable on our website for free, and you can actually get in there and write your own plugins as well. Part of the airborne post-processing tools are not included in that version, so it's not open source at this point, and I don't think we plan on going that route. But you can explore and try the software for free if you want. So you can download the software and also some sample data cubes and play around with that. So,
Okay.
yeah.
So Pixhawk is it's the control set for a lot of UAS, similar to ArduPilot or Piccolo in
A
nature.
control set.
Yeah, it's what you use to program the drone. So if
Oh,
you a lot of
yeah.
something like Parrot or DJI or the
Hmm.
integrated solutions, they don't necessarily give you that capability.
Oh
But
yeah.
there's a lot of solutions that are very customizable, and that's where Pixhawk, Piccolo, and ArduPilot is it's an open source, completely open source environment for developing controls for
Yeah.
actually multiple platforms, rotary wing, fixed wing, even ground and
Oh
uh,
yeah. Well, so you see, my ignorance of that is a good demonstration of how we don't deal with it so much. We and our system is really independent of the platform, and so we just say, here it is, put it on anything that flies, and you'll get some data, right? So that's been kind of our model. It's not that you don't want absolutely to go into flying drones and figuring that out, but you just have to kind of pick your battles and say, this is we're going to be good at, and we're going to partner with other people to do the other part. And that's an opportunity for people like you. So yeah.
excellent. Well, I think it was Seth that had a question, or Dan. I'm not sure.
Hey, good evening.
Hi.
Appreciate the presentation. Fantastic.
Good.
Bozeman rocks. Very cool place.
It's a it's a nice place. We're
Yeah,
lucky to
yeah,
be
big
here.
fan of big sky country, beautiful place. Hey, I got a couple questions for you, man. In regards to, I'm going to come at this from a few standpoints as a commercial drone service flight provider, as an
Okay.
operator in the military, and as an academic. Sorry. RTK versus non-RTK. How is let's get back to the point. In orthomosaic mapping and imagery, it takes millions of data points, puts it into a big array. How does hyperspectral imaging support and make that point cloud build out better?
Okay, you broke up a little bit when you were asking your question, but think in terms of mosaicing, when we mosaic images, we don't typically mosaic an entire hyperspectral data set. So we will take your images and you can do your classification, your analysis, and create a a TIFF or a PNG image or a TIFF image out of that, and then you can go ahead and mosaic that. And we have the ability to do that, but ours just uses basically the geolocation and the shape, of the image to overlap them and just stack them down in there. So I think it's not what you were doing, but I like I said, I missed part of your question. So if I didn't answer it correctly, ask again.
Totally. Sorry for my connection. It is dinner time in the background, so I apologize for the random noises. Um, in terms of data point collection and assignment, orthomosaic imagery collects tens of millions of data points and puts them all together. How does hyperspectral imaging support and create more or less? I would imagine it would be less, but how does it create more data points to support orthomosaic compilation?
So what data points are you talking about? Like, is this, I
For
guess I,
example, I'm gonna put two different systems out there: LiDAR
mhm.
and my camera on my
Okay.
drone.
Okay.
Um, and when they collect data,
Hmm.
and I'm sorry, I should have referenced this. Most of my work with drones is over large construction areas where I'm looking at dirt being moved and
Yep.
creating as-built and baseline mapping for home builders.
Okay.
So, 50 to 350 acres. This is a fantastic product, and I remember working on this about 10 years ago with hyperspectral payloads with In-Situ and Boeing, with
Hmm.
one of the programs of record, which is the RQ-21A Blackjack system. Hyperspectral was the big buzzword 10 years ago in the military, and now that it's been developed on the consumer civilian side, how does that create more data points with
Yeah.
a LiDAR versus regular camera captures imagery? And how does hyperspectral imaging go into those two applications and improve it overall?
Yeah. So I guess I could think of a few ways to do it. The thing is that your hyperspectral data cube, for every pixel, for instance, if you're using LiDAR, you're doing basically creating a elevation map. And
Right.
so you're saying at coordinate XY, elevation is H. Now, for us, we're saying at coordinate XY, we have this entire spectrum for you to do something with it.
Right.
And it's probably more than you can deal with if you're trying to merge that in with your elevation map and whatever else kind of data that you have. And so probably what you do is that you pre-process, basically get what you can out of the hyperspectral data. So for instance, for each of those spectra, you'll classify it. You say, this spectral signature tells me that at this point I have this pixel represents a spruce tree. And then this pixel over here represents a pile of dirt. And this pixel over here represents grass. And so you create these categories and decide what's there, at least in the way that you can describe what's there. And you might also look at clusters of pixels and say, oh, all this whole cluster here, that looks like the crown of a oak tree or something like that, right? So you can tell it's an oak tree there. And then you're going to have to find your own solution to say, okay, it's an oak tree, but how tall is it? How much wood is in this tree or something like that. But you'll get that extra information. And some users have done that. There's a couple of research group in China, for example, who use the combination of both. And you either fly two separate missions and then merge the data, or you fly it all in one mission, but you kind of going to have to probably pre-process afterwards. You can't, it's just too much to process in real time. But they use both the size of the crown of the tree and the shape and the hyperspectral signature all together to really positively identify what's there, and then and the size, etc. And they use that also for carbon mass, how much material is in there or something like that, how much tree and what's the word I'm looking for, organic material I have here or something like that. So it's just one more data point that you can use. But you're probably gonna have to process it first to decide what you want to apply. What do you want to assign to that pixel? Do you want to assign a tree species? Do you want to assign a water content? Do you want to assign? There's all sorts of things that you could potentially extract out of the hyperspectral data, and then you can go ahead and process that with the rest of your information.
Perfect.
Does the
I
hyperspectral imaging, does that pick up, you mentioned chemical, can that differentiate, say, like off-gassing from a tree, like VOCs or anything coming out of even vapor?
So we're actually working on a dedicated imager right now to look at methane, because that's an important thing. Um, it gets difficult. Like there are some limitations, and a lot of times you have to try it. Like you say, okay, let's look at the data we can get and see, can we get the contrast that we're looking for or not. And but I will say one thing is that if you are looking at a gas that is fairly transparent in the wavelengths that you're probing, then what you're going to see is mostly what's behind the gas is the background. So the light's going to go right through the gas, bounce off the surface of the earth or something like that, and back through the gas, and that will affect your spectral signature a tiny bit. But still most of your spectral signature is due to the surface that you're bouncing off at the back. So my only point is that hyperspectral imaging is good at differentiating two chemically distinct things, but not so much at detecting trace amounts of something on a background that's something else. because then it gets lost in the overall signal.
Okay. Does anybody else have any other questions relating to hyperspectral imagery or the utilization of UAS to carry it as a payload? Oh, it looks like Dan has one over in the chat. Since hyperspectral imagery can detect variations of reflected light, which cannot be perceived by the human eye, and most examples are grouped or solid images, could this technology also detect atmospheric variations, such as humidity or pressure variations?
Humidity, yes. If you have enough, like if you're looking at a big
Moisture.
enough volume of humid air, in the infrared especially, there are some very distinct absorption bands for water, and so the infrared is really good to detect water, even water content in organic matter in trees or leaves or something like that. So you'll have basically the same spectral signature for a leaf that's well hydrated and one that's not well hydrated, but you should be able to see clouds as well, and not every instrument will be adapted to every application. So some of our instruments actually work in the visible range, so you don't see outside of what the eye can see, but you see that that specific range with a lot more detail, and that can give you more information. So
Okay. I assume pressure might be calculatable off
pressure,
of the particulate material and the the
yeah,
the
it's
motion.
not
I mean, you'd have to do it.
obvious to me right now how you'd look at pressure. It
That
might be
would,
possible, but yeah,
I'm thinking that would
it's not a
require,
gimme.
yeah, no, complex calculation, use a machine learning
Yeah,
potentially to examine it
yeah,
over time.
yeah,
Um, and you'd have to, there's a lot of data you'd have to know, a lot of control
yeah,
points, but
yeah,
I'm
yeah.
not going to say it's impossible, improbable.
Yeah, right. Yeah.
Excellent. Any other questions here? This has been great. Oh, Roth, please.
Can you hear me, Brent?
Yep.
Brent and Alex, thank you both so much for taking time to set this up and invest your time in us as students. So my question is, how much of a hindrance is altitude on resolution, and how do you kind of fill in the gaps? So I assume that part of it is scaling your sensor for the altitude, so you have a more capable product. And do you use machine learning to kind of fill in the gaps, or how's that work?
Okay, so in terms of resolution, basically, if you go twice as high, your field of view is set. It's an angular field of view. So if you go twice as high, you see twice as wide, but you still have the same number of pixels. So your resolution is dropped by half, and that's just what you have to live with. And so, or you can use it your advantage. If you want to see more, you can fly higher, but you lose some resolution. You can all use a different objective lens. So we have different focal length lenses so that you can bring it back and keep your resolution even though you're flying higher. Although you get to some limitations there, because if you're looking at a very tiny spot, then stability becomes an issue. So for airborne applications, typically we say don't go to a longer focal length than 17 millimeter with our visible range imager. We just say that's a good length. If you try to go higher, maybe the georectification process will not be able to account for the jitter. And then for filling gaps, I think I understand your question. Like if you're flying and you're doing a little bit of this, like maybe you missed a pixel somewhere, and so you can end up with a data set with some blank spots where the georectification says, I never found a time where that spot on Earth was imaged, and so I have nothing. But to mitigate that, what you do is that you oversample. So you take more frames that you need to based on your flying speed to try to make sure that you get everything filled in. So that's one thing that you typically do to make sure that you don't have gaps in your data. And there was something else I was thinking about. I forget now. But does
Perfect.
that answer your question?
No, that was
Yeah.
excellent. Thank you very much.
Okay. Yeah.
All right. Well, with that, I would like to just say thank you to everybody for joining us tonight, as well as a major thank you to Alex for sharing his thoughts and expertise regarding this technology. This has just been such an informative session, and it helps us to better understand the challenges as well as the opportunities that are associated with the incorporation of hyperspectral imaging technologies into UAS and other uncrewed system platforms. I hope to have a recording from this session uploaded to the Instructor Corner by tomorrow. And once again, thank you everybody for joining us.
Thank you all, and good luck.
Thank you.
Thanks, Alex and Brett.
Take care.